Okay, so our next speaker will be Krishnendu Sengupta from ICS Kolkata, and he's going to talk about roots of violation of ETH in periodically driven quantum systems.
Okay, thanks everyone for attending this talk, and I would like to thank the organizers for organizing this meeting and inviting me here. The title of the talk today would be Roots to Violation of Eigenstate Thermalization Hypothesis in Periodically Driven Systems. And this is a bunch of work that I have done with lots of collaborators, and Arnav is here at in the audience. So Bhaskar is now, Bhaskar and Shomshubro were my students who are currently, well, Bhaskar is currently a postdoc. Annesha was a postdoc who is now a faculty member in Kolkata, in Bengaluru College. And Indranil Paul has been a longtime friend and collaborator who works in Paris. And if you are interested in any of these are some of the references which one can look at. So here is a brief outline of the talk. So first I'm going to very briefly touch upon Eigenstate thermalization hypothesis and talk about possible routes to violating it. And the two of the things that I'm going to particularly focus on are quantum scars and Hilbert space fragmentation. And these are two known routes of violating ETH in a interacting many-body system. The topic of the talk could be that if I periodically drive such a system, can I realize this phenomena? And okay, if I can realize this, and if so, what are the signatures? So, okay, this is probably not so relevant for most of the people here. I mean, they already know it. So, but let me just go through it quickly. So if I consider a generic quantum state of a non-integrable many-body system, I know I can write it as in superposition of the eigenbasis. And then if I take an operator and try to find its expectation in this time evolving state, I would find the following form. Now, where OMN is the matrix element of this operator between any two states. But the moment you look at it, you realize that there is a problem here because it's not consistent with thermodynamics in the sense that if I now first, let's look at the steady state behavior of this, and that occurs when I can ignore this off-diagonal matrix element. But clearly here, the steady state relies on the initial overlap, this CMs, and therefore you tend to believe that ergodic systems written in memory of the initial state, which you know doesn't happen. That's one problem. And the second problem is that it takes an incredibly long time to reach this steady state, which is also something that we do not see in a generic quantum system. And the reason why it takes so long is this difference of this energy gaps in this many-body quantum system. So you see that I can neglect this matrix elements only when my time is larger than inverse of this energy gap. But in a non-integrable many-body system, especially at the middle of the spectrum, this energy gap is exponentially small in system size. And therefore, you would conclude that you would take an exponential to the power L order time to reach steady state, which of course is not what we see in practice. So it turns out that if you would have invoked random matrix theory and would have said that, well, this matrix element are something that I can get out of random matrix, then these difficulties go away to a certain extent because then your off-diagonal limits are 0. You don't have to really worry about this. And you see, if I put this OMM to be some random number O prime, then the initial memory is also gone because it's just mod CM square which goes to 1. So, however, this doesn't agree with standard numerical result because you don't get an energy dependent answer, which we know happens from thermodynamics. So in this context, to cure this problem, there was a hypothesis which was initially due to Sengupta, Deutsch, and a lot of other people who has worked quite hard at it, and Anatoly and others, Marcus and others. I mean, they wrote a very nice review about this, which I completely recommend if anybody wants to pick up details. What it says is that there is a generalization of these random matrix errors, and the matrix elements are not completely random, but they have the following form. So they have a diagonal term and an off-diagonal one, which is exponentially suppressed in system size because this entropy is an extensive quantity, this S. And if you take this and plug this back in, depending on the energy, for the fact that the energy fluctuation of a many body system is sub-extensive, you can show that you get back the microcanonical ensemble result, and for that matter, the canonical ensemble because of ensemble equivalence. There are some very straightforward algebra that one can do to get this. I'm not going to get into the details, but it at least cures some of the problem. Okay, and this happens to be almost omnipresent because for any ergodic system, thermalization occurs, and this prediction of ETH has been checked and verified to quite some extent. However, one thing that ETH relies on is the ergodicity. Your system got to be ergodic, and therefore violation of ETH happens when ergodicity is lost. That can happen in integrable model and can also happen in many body localized system if they exist. However, I'm not going to talk about these two. What I'm going to talk about is the violation of ETH by two not so obvious ways. One of them is when it gets violated weakly because of presence of a special class of eigenstates in the Hilbert space of a many body system, and this leads to long time coherent oscillatory behavior rather than a thermal decay. And these are the quantum scars which I'm going to talk about. And the second one is this violation of ETH due to fragmentation of Hilbert space, which leads to loss of ergodicity. This Hilbert space fragmentation also has been discussed recently in quite great details, and I'm going to introduce it a little bit for the necessity of my talk. So let's just talk about quantum scars. Okay, so the simplest way to look at quantum scars is to think about, so let me just give an example. Okay, so let me think of a model which has a XY part and a SZ part. These are spins interacting by nearest neighbors, but these are spin one objects. So the local basis is plus, minus, and 0. And this is taken from this review article, which is a very nicely written one. So you can think of the ground state of this system, and in certain regimes, this could be the two polar states. For example, any of the two polar states, let's say all minus. Okay. Now, if you think of excitations over these states, one possible excitation is to create a single flip spin and take a superposition of that, and that very much like the Ising model in a transverse field gives rise to a particle band. That's kind of straightforward. But here, that's a single Magnon state in this language of spins. But here, it turns out there is another type of excitation, which is these two Magnon states, which is particularly interesting. And let me tell you why. So suppose I take this operator, J plus minus, which depends on this two operations of S plus or S minus. So if you have a down spin, it first takes it to 0 and then takes it to up. And this is done with a opposite sign or a pi phase at the odd and the even side. Okay, so that's my operator J plus. Now think of acting this operator. Let's just talk about acting it once. Let's just take n equal to 1 here on this state. What it does is to create a plus minus pair because on the side where it's acting, it just gives a plus on a otherwise minus this all down background, minus background. But if you look at it, these kind of terms, which are the nearest neighbor interaction between spins, they work with these plus minus terms to give two zeros at neighboring sides. Okay, because one of the S plus is going to flip plus to 0, and minus to 0, and the other S plus is going to flip plus to 0. So they get a pair of two zeros. But if you do it with a random sign at odd and even side, then the total answer is 0. So these are 0 eigenstates corresponding to this part of the Hamiltonian, and therefore you get a tower of states which just depends on this SZ. And this forms a exact tower of eigenstates. So this bimagnon states yields a separate tower. And this is an example of a spectrum, what is typically called a spectrum generating algebra, where this Q plus is now your J plus or J plus to the power n or some such stuff. However, the interesting part here is also that if you define an operator Jz, which is just the sum of these Sz operators at different sides, it turns out that this bimagnon operators forms a SU2 algebra. And they form a spin L by 2, where L is the system size representation of this SU2 algebra. And therefore, this leads to an emergence of extra SU2 symmetry within your otherwise thermal blob of states. And this is what leads to ETH violation, because just imagine that if you are starting from an initial state, which essentially has a large overlap within this sector, let's say it belongs to this sector, dynamics will, because of this SU2 symmetry, will make it go around within states of this sector. And you could easily have an oscillatory dynamics, because this is an order L subsector, not an order exponential L subsector. And one can calculate different things like correlation functions and entanglement entropy and stuff like that. All of this deviate from their ETH prediction. So this is a weak violation of eigenstate thermalization hypothesis. And reason it's a weak violation is that you need to start from specific initial states. Otherwise, you don't see this. Yeah, please.
Spin 1 XY chain with open boundary conditions, then you have a hidden SU2 symmetry. And then your scarce states can be thought of as kind of irreducible representation of that hidden SU2.
I'm sorry, hidden SU2. And
so
what representation? Can you just...
Irreducible.
Okay.
Just you can think of the scarce as just a big spin, right? In that hidden SU2. Of course, if you are considering periodic chain, then yeah, you're totally fine. But for the open chain, so what I wanted to say was, you can't think of your state as scarce.
Okay, so if I remember correctly, in that review paper, they were talking about a periodic chain, but I would like to understand this boundary condition issue a little better. I don't have this at the top of my head. So yeah, thank you for that comment. But let's think of a periodic state and yeah. Okay, but yeah. Yeah, that you can pick, of course, sure. And then, so these cars, the signature of these cars first came in when, in the context of Rydberg chain in experiments. So I'm not going to talk about these Rydberg atom systems anymore because David gave a really nice introduction to them. So all I wanted to say is that if you have these two atoms which are connected by two levels which are connected by these different lasers, what happens is that the effective Hamiltonian for describing this is the following. So you can create a small detuning, which is essentially the difference in energy of the sum of these two laser frequencies with the the energy difference between the ground and the Rydberg excited state. And that detuning comes here. So it's like a chemical potential for this Rydberg excitations. And then because of this laser process, it's a two-photon process, you get an effective coupling between the ground and the Rydberg state that comes with a sigma xi that just connects between the Rydberg and the excited state. And then, of course, there is this dipolar interaction, which essentially tells you that if you have two Rydberg excitations at sites I and j, there is a strong dipolar repulsion between them. Okay. So, so now, if you think of it in terms of this Hamiltonian, you could ask that what's the ground state of this system? Well, in the limit of large negative delta, you don't want to form any Rydberg excitations, and so the ground state is just the ground state of these atoms. But if delta is large and positive, if you put a positive detuning in this language, what happens is that the system, of course, wants to form as many Rydberg excitations as possible, but they cannot because of this competing dipolar, competing interaction between the atoms. And if this happens, and if you are in a regime where the dipole interaction is super strong between the neighboring sites, but not so strong in the other sites, then you can have a Z2 symmetry broken state where the system is going to form this Rydberg excitations at alternate sites. If you make this a little stronger, you could form a Z3 states where two states are excluded and so on. And this is one of the things that they saw in this experiment from Marcus Grainer's group. But interestingly, what they saw is that, so they had this Z2 ordered state. So they started from there. Then they quickly quenched the system to this disordered phase where there is no ordering anymore. And they quenched it to a point where this detuning is very close to 0. And then they wanted to see how this state evolves. And they found this long time oscillatory behavior rather than the expected quick thermalization, because this is an, after all, an ergodic many-body state. So non-integrable many-body system. But this was subsequently interpreted in terms of presence of quantum scars in the system. And it turns out that in this kind of models, these scars are approximate. So you have this oscillation for certain times and then they decay. But this is roughly the experimental signature of these scars. So to talk about the Rydberg model a little bit, because it's going to form a part of my talk, what I want to say is that I can write it in different languages, but the spin language which I'm going to use has the following mapping. So the Rydberg excitation number density is m, okay, at a given site L, and that's related to the spin by this stuff. And I can write this sigma x or sigma y as, in terms of some bosonic operators if I need to. But in terms of this, I can think of this Rydberg chain as in the spin language as this, okay, where sigma z can be replaced by this n because it's just a constant shift. But now if I want to impose the constraint and be in a regime where this where this potential between the neighboring sites is large compared to other scales in the problem, I can impose a constraint saying that I'm only going to flip a Rydberg spin if I have two neighboring spins to be down, so that I don't have two spins on the neighboring sides to be up at the same time. This constraint can be implemented by putting a projection operator, which is local, because it just forces the spin to be in the neighboring sides to be down. And then within this subspace, we can look into the properties of the spin check. And that's supposed to mimic the properties of the Rydberg atoms. Okay. So now I'm going to come to the part of the talk, which is our work. So we wanted to look into what happens when we drive this system periodically. And the particular question that we were interested in is that, of course, we know that such driven system is described by the Fluke Hamiltonian. So the question we asked is that if there is quantum scars present in the spectrum of the Fluke Hamiltonian of the system, and if so, how do they? What's the signature of this in the dynamics of this driven system? So to do this, what we did is that we took a this Rydberg spin model, and we varied the sigma z term or the n term, which is the detuning term, from plus to minus lambda between two cycles. So it's a square pulse protocol. In the first cycle, it's plus lambda, and the second cycle is minus lambda. And then we wanted to look into the evolution operator of the system, which is given by this. And this is straightforward. Numerically, you can then diagonalize, h of lambda and h of minus lambda and do some matrix multiplication on finite size to get the evolution operator. What we are particularly interested about is the density-density correlation function, the time dependence of that. So the point is that knowing the eigenvalues and eigenfunction gives you a numerical handle on the Fluke Hamiltonian of the system, because we can calculate E. That's numerical, okay? However, we can also do some analytics, especially in the regime where this drive amplitude is large. And that what we use is something we call Fluke perturbation theory, but you can also call it doing Magnus by going into a rotating frame. It's really one and the same thing in this context. But what we do is the following. So we say that my drive amplitude is large. So 0th order, I can just keep the lambda term and found the 0th order evolution operator. And if I define my state in terms of the number of upspins that I have, extra upspins that I have in the system, then the expectation value of this evolution operator is just this, okay? It's diagonal in this basis, and its energy is given by this e to the power im lambda t, etc. Now we use standard perturbation theory, which is found in textbooks. At least first order thing is really easy to do. And you calculate U1, which is some perturbative calculation. And at the end of the day, this gives you a first order Fluke Hamiltonian, which, if you see, is very much like a original Hamiltonian with lambda equal to 0, except that it's in a rotated basis with this rotation angle being gamma. And importantly, the amplitude of this now has a sine gamma by gamma factor. So it tells you that this Fluke Hamiltonian, the first order Fluke Hamiltonian, which anyway in the large frequency and large amplitude regime is supposed to control the physics of the system up to a very large pre-thermal timescale, is going to go to 0 whenever gamma goes to some integer multiples of pi. Okay, and there the entire physics is going to be dominated by higher order terms. So what do you expect? So at those special frequencies where the Fluke Hamiltonian doesn't have this, PXP kind of structure, not say the sigma x tilde, etc., I wouldn't expect quantum scars in my eigenspectrum of the Fluke Hamiltonian, because that's some very complicated higher order spin model. In fact, we calculated that 3-spin term, but that's different. So that's typically not going to have these scars. However, in the high frequency and high amplitude regime where this term is not equal to 0, away from this special frequency, I can expect some quantum scars because it's going to be in the eigenspectrum of HF1, just because it was in the eigenspectrum of the PXP model. This HF1 is just some modified PX1. And therefore, I would expect that the behavior is quite different, the behavior of the correlation function. So here we plot the behavior of this correlation function. So at high frequency, as we expect, this is this scar-like oscillations. And these oscillations show up if we start from an initial Z2 state, which is an antiferromagnetic state like this. However, if I start from the Rydberg vacuum, that's the red line, and you see that ETH prediction holds there. Because, and this is why this is a weak violation of ETH, because you need the right initial state to see the violation. But if you go to very, very small frequency where there is no local Fluke Hamiltonian and things are really, really not determined by any kind of perturbation, you don't expect this kind of scar behavior to come and you get ETH result, okay, for both the Z2 and the 0 state. However, in between, things get in and get out of this scar and ETH type of phases. And you see here at omega equal to 1.3, I find this ETH kind of behavior. Omega equal to 0.5, I find scar-like behavior, and so on. And this, one of the predictions of the first order Fluke perturbation theory is there is going to be multiple frequencies at which this ETH-like prediction is going to hold. And so there are lots of reentrant transition between coherent dynamics and ergodic thermalization. So let me not get into the details of this more, but here is what happens when we are close to a special frequency. For example, when we are, say, at a frequency where the first order Fluke Hamiltonian is going to go to 0. So this happens at 7.75 in some weird units for us. But you see that when I'm higher than this, when the drive frequency is higher than this, I see these star-mediated oscillations for the Z2 state. As I go towards the special frequencies, these scars become unstable, and you really see that this goes towards the ETH value. Here there is all the rapidest thermalization. There is perfect ETH here, and here the oscillations come back as you lower the frequency. So it's really non-monotonic. In both sides of the special frequencies, you have these oscillations, and concomitantly, what we can see is the half-chain entanglement entropy. At this range, so let me just show it in the previous slide. I'm sorry. Here, at high frequency, you see this band of scars out here. And these are also the systems with largest overlaps with the dynamical state, which is given by red dots out here. But at small frequency, everything has gone into a thermal band. That's the high entanglement band that you have, which is volume law entanglement. Here at 0.5, there are some states out here which has come down from the band out here. It's not very clean, but it still see this band of states, which is away from the thermal band, giving rise to these oscillations. But at 1.3, which is a higher frequency, mind you, everything has again gone back to the thermal band. Okay.
I have a question.
Yeah.
So here. Here.
Yeah, sure.
So actually, there are two periodicities, right? One is the periodicity of the drive, and then there is the revival periodicity of this. So how to read this graph? in terms of these two?
This frequency is a complicated combination. So at high frequency, I can say that the periodicity is the star periodicity of HF1. But in the lower frequencies, this effective Hamiltonian, which is giving rise to these stars, is completely different. But in here, you see that this difference in energy, that roughly gives this periodicity out here. Here, it's much more complicated because there could be multiple frequencies and stuff. But it's really the energy gap between these different scarce states which sets the periodicity of the solution. Yes, of course. That's there, sure. Yeah. Well, okay. Yeah, sure, okay. Okay, so the idea is that by doing this, you can tune between ergodic and scar kind of oscillatory behavior. And here is a phase diagram for that, where you have these spatial frequencies in the lambda omega d plane. That's the drive amplitude, and that's sort of the drive frequency. And we are always at the high lambda plane. And this essentially tells you that at high frequencies, there are wide regions where the coherent oscillations would be. And then these thermal regions, which are the special frequencies, just becomes too numerous. And at lower frequency, this completely fills up the entire space. Okay. So that's sort of a possibility of tuning coherence in driven many body systems. And that sort of is the phase diagram. However, it turns out, and this is something we found a little later, Arno would probably recollect, this happened after the first set of work, right? Yeah, during COVID. So what we found is that not everything is as well understood as we thought it was. Because suppose now I look into this correlation function by starting from the zero state, that is the Rydberg vacuum state where all spins are down. And I just try to look into this and see if ETH prediction holds. And at high frequencies, and also at reasonably high frequencies, I would say perfect points. I would say that it obeys ETH very well. However, when it comes to lower frequency, it does some weird behavior. First, it assumes a superthermal value, which is a deviation from ETH. Then it goes down, and there are some particular frequencies, this 4 and close to 4 and 8 out here, and integer multiples of some gap, where the system doesn't evolve at all. It's an example of a dynamic freezing. And there are quite a bit of wide region in between these, where the system reaches a steady state, but that's way different from what ETH predicts, and it's a subthermal steady state. So these, as we saw, are different scarce states that does the dynamics here. I'm going to show you some pictures, but the point is that in the Fluke version of this, because of the presence of these higher order terms, you can have scars which have no analog to their equilibrium counterpart. And here, this is sort of time evolution of this correlator, again, stroboscopic time evolution. So in the high frequency regime, we find ETH predicted thermalization. However, when you lower the frequency, there are these oscillations. And mind you, these are very different from oscillations of the Z2 scars, because we are starting from a zero Rydberg vacuum state, which has zero overlap with the Z2 sector. So these are really different states. And then there are special frequencies at which the system doesn't evolve at all. And this is exact numerics for L equal to up to 26, I believe. And then there is a parameter regime, a range of frequencies, where the system reaches a steady state which has subthermal correlator values. And each of these has a separate explanation, but I don't have time to get into that. I have to go to the other part of the talk. But all I wanted to say is that in the region out here, there are coexistence of the Z2 and the zero scars. The Z2 scars are given by these green dots out here. And these are the ones which influences your dynamics, gives you oscillation, provided you start from a Z2 initial state. However, there are also these set of scars, which gives you these oscillations, provided you start from a vacuum initial state. And these have no analog in the equilibrium setting. Okay. So now let me switch gear and go to the other type of violation of ETH, which comes from this strong Hilbert space fragmentation. So this again is a very developed subject, and I'm not going to do justice to introducing it, but let me just take a couple of minutes to do that. So what it means colloquially is breakdown of Hilbert space into an exponentially large number of dynamically disconnected sectors. What it means is that you have groups of states in your Hilbert space, which is not connected to other groups, and this is not the usual case for thermal systems, okay. So this fragmentation is usually observed in a computational basis, and it's important to point that out because if I'm in the eigen basis, then everything is fragmented. It's just single states with no connection. That's not what I mean. I mean that in the computational basis, there are these chunks, which are disconnected from one another. So the other thing is that such a separation of Hilbert space into dynamically disconnected sector is very different, which happens due to global symmetries. Because if you think about it, in a Hilbert space, you write it as a matrix, but you can project into symmetry sectors and work with those. Those global symmetries we know reduces the size of my effective Hilbert space and gives me a lot more computational power. But the number of such sectors never scales exponentially. Okay, those are just a few sectors that might increase with system size, and that's it. So for strong Hilbert space fragmentation, which is what I'm going to talk about, if n is the largest fragment and capital N is the total Hilbert space dimension, it turns out that small n by capital N goes as exponential of minus L, where L is the system size. And this separates strong Hilbert space fragmentation from other kind of symmetry separated sectors. And you see that this in turn means that there are exponential number of such sectors in your Hamiltonian. Okay, if the largest chunk is exponentially small compared to the total Hilbert space, then there must be exponential number of such sectors. So quantum scars, what I talked about, can be thought about as a weak Hilbert space fragmentation, where this ratio goes to 1. Okay, that's one way of saying it. Okay. And there are lots of models in exhibiting strong Hilbert space fragmentation. Most of them are 1D models, but I would like you to point to a recent work of ours, which gives an example of a 2-dimensional model which exhibits strong Hilbert space fragmentation. This was there, which came out recently. So what are the signatures? One of them is memory retainment. Okay, so if you have this fragmented Hilbert space, one can show that if you compute something like an autocorrelator, which typically goes to 0 in a ergodic system, it doesn't go to 0 here. It's always above a certain bound called a Mazur bound, but I'm not going to get into the details of that. But it's finite. Let's just put it that way. Okay, and the precise value of this and the calculation of this bound has been done in Frank Polzmann's group by invoking some statistically localized integrals of motion, which works with this fragmentation. Again, I'm not going to get into the details of that, but this bound is quite well understood, in my opinion. However, the point that I want to make is that a signature of this Hilbert space fragmentation is that autocorrelation function at long times is going to have a finite value, okay, greater than a certain bound. Also, if you look into the entanglement entropy of this kind of systems, if it is thermal, it has a value, right? That's given, and the maximum value, which is typically called the page value, and that page value is just the logarithm of the dimension of the largest symmetry sector. Okay, if you are doing it in a symmetry resolved way, right? Minus some constant, of course, but that's not very important. However, if your state is confined within the subsector, that value is going to be the page value of the subsector and not the total Hilbert space. So there is a deviation of the entanglement entropy from the symmetry resolved page value. So these are the two things which are going to be important. So let me again give an example of a model, and I'm going to go through this very, very quickly because how much time do I have? 5 minutes? Okay, so maybe 2 minutes extra. We'll just go through this a bit. So, so there is a fermionic model with correlated hopping. Many people have worked on this model, and this is one of the papers, for example. So where there is the hopping is done with a projection. Okay, so the hopping can take place only if the occupation of the second neighbor to its right and the first neighbor to its left are identical. And this means, what this means is that in this chain, if you do a hopping like this, you don't change the number of bonds with two occupied sites at the ends, which means you don't pay an energy cost of G. Okay. So this is why for the strong Fermion chain in the strong V limit, this is the projected Hamiltonian. So you go to one of the sectors, okay, and it turns out the first thing you see that there are many exponentially frozen states, which is a signature of this Hilbert space fragmentation. This is one example. This state here, the fermions cannot move by this projected hopping. And this exponentially many frozen states is an example of, is a characteristic sign of an Hilbert space fragmentation, although it's not necessary, but it's seen in a lot of models, including this. But there are other dynamical states where states can move, but they're going to move within a given subsector. So how do we see that there are exponential number of such sectors? First, let's do some counting. So number of states in the largest symmetry sector, one can count them to be 2 to the power L by L. Let me skip this counting procedure because I'm running short of time. But let me now tell you just a little bit why there are exponential number of states, how we can see this. So think of a site, let's start from a frozen configuration like this and divide it into L by H sectors. Okay, and here I've shown this picture for L equal to 24. This is again taken from this paper by Thomas et al. And then within each of these, I can do two things. I can leave it unchanged, or I can introduce defects, which corresponds to movement of these to the nearest part and that to the left part. Okay, these are the defect A's and B's. So out of these, each of these, I can make many other states with 3 other possibilities. Okay, I can sort of keep this like this, or I can introduce 2 of these defects. So how many states are there? The answer is 3 to the power L by 8. And because only states with same numbers of defects are connected by H, this projected Hamiltonian, these states gives a estimate of the number of states which can in principle be connected. However, you would see, and this is something I don't want to get into the details of because of lack of time, is that Hamiltonian can at most connect only L of these states out of all this. And therefore, the total number of fragments which are not connected by the Hamiltonian is exponential in L. Okay. And this argument is something I don't have time to get into, but I can discuss at the end of the talk. So now the last part of the talk, which will take 3 or 4 minutes. So recently what we found is a pre-thermal signature of this strong fragmentation, that is getting the strong fragmentation physics out of equilibrium, and that's what we're going to tell you right now. So the good part about this is that you can start with a simple driven fermion chain. So the model is really simple, and you drive the chain by changing this V1, which is the nearest neighbor interaction, as a periodic function of time. You can do this for any protocol, either the cosine or the square pulse or whatever. It really doesn't matter. And in the high drive amplitude limit, if I do a calculation similar to what I showed for the quantum scars, that is the first order Fluke Hamiltonian using Fluke perturbation theory, I find that the effective Fluke Hamiltonian is given by the hopping term of that is given by a term like this, where AJ is just this difference in occupation between the second neighbor at the right and the first neighbor in the left. So in fact, at special frequencies given by this gamma naught, where special frequencies which is given by this, it turns out that this term, which is this product of f gamma naught, which is either a Bessel function or a sine function for different protocols, there are special frequencies where this goes to 0. At these frequencies, it turns out that the hopping part of the Hamiltonian is exactly same as the projected Hamiltonian that I showed. And therefore, one expects that in the so if you are in the large drive amplitude regime, where you have a long prethermal regime, so you are going to see signatures of Hilbert space fragmentation in that regime. And this is precisely what we saw. So let me walk you through these plots. So first we looked at the entanglement entropy. So the page limit for this is given by log of the dimension of the system, and the space limit of a given fragment, that is a fragment of HF1, is given by log of d of this fragment. Okay. So in this particular case, we took out a state from the largest fragment, and we drove it at a frequency which is one of the special frequencies. So you see, as I increase my drive amplitude, this entanglement entropy saturates to the page value of the fragment and not of the entire system. However, if I do this at a frequency which is away from the special frequency, it always saturates to the page value of the system. So this tells you, oh, just 2 more minutes. Okay, sure, thanks. So this tells you that, in this drive frequency, I'm seeing something special. My entanglement entropy is deviating from its page value. And also, if I take a random fog state from this Hilbert space, and I drive it with a large amplitude and at the special drive frequency, depending on the fragment from which I pick it up, it goes to several different page values, which is a clear signature of Hilbert space fragmentation. This cannot happen otherwise if you take random states. And also this autocorrelation function, I already told you that if I am in the fragmented limit, there is this stuff that it has a finite value. You see that here I drive it with the special frequency, and as I increase the drive amplitude, it goes to a finite value at long cycles. That's the pre-thermal fragmentation for you. However, if I do this at a different value, which is this red curve, then you see that it basically goes to 0. Okay, it just tends towards 0 for long. Now, the point is, and so this is the phase diagram. In this part, there is this Hilbert space fragmentation regime where this thing shows a finite value, and the rest is pretty small. We also estimated how this number of cycles which the system takes to go to the ETH predicted value, and that increases exponentially with the drive amplitude, which is also expected because this is not too different from driving it at high frequency. And what is exponential of omega in this Magnus work now becomes exponential of V here. Okay, so that's the explanation. And finally, for the last 1 minute, there is something in this realization of Hilbert space fragmentation in out of equilibrium, which has no counterpart in the equilibrium part. And one of them is this oscillation of frozen states. Because if you have a perfect Hilbert space fragmentation, states are frozen, they don't move. Here, of course, they are never frozen exactly, because the higher order terms in the Fluke Hamiltonian always induces a dynamic signal. But it turns out that if you start from a Z2 state and you do this evolution, the system goes to sectors with, so this Z2 state is a state where there are no defects, meaning that there are no states with 2 particles being on adjacent sites. So that's your definition of defect. So that's ND equal to 0. But the dynamics carries it through higher order terms to other sectors. But because of this fragmentation term, a substantial part of this state then comes back to the other side, which is this Z2 bar state. And therefore, there is an oscillation between this Z2 and Z2 bar, which is the oscillation timescale is determined by the higher order terms. And it's just the energy split between the bonding and the anti-bonding states of this Z2 and Z2 bar. Okay, one can show this thing. This is, of course, a violation of ETH. That's pretty clear from here. You're going to see a violation of ETH even if you start from a random frozen state, but you need this extra Z2, Z2 bar symmetry out here to get these coherent oscillations. So these coherent oscillations are a signature of Hilbert space fragmentation out of equilibrium, which do not have an equilibrium analog. So I'm out of time, and so I'm just going to put my conclusion slide and stop here. Thank you for your attention.
Are there any questions?
Yeah, Duncan.
What sets the width of these regions where you get these scar states? And I mean, it's you might expect that it would be very narrow, but it's not. It takes up a finite region of the.
Well, you see, the width of
the sort of parameter space where you.
Yeah, the exactly. Width of these dark regions.
Yeah, yeah, exactly.
Well, you see, the point is that these dark regions are not the regions where there are scars. This is the opposite.
Yeah.
So the point is, the spacing between this dot region, that's set by this when the next zeros of the sine function comes in. You know, the sine lambda by lambda, when they go to 0, where lambda is equal to n pi, okay? So that's where these dot regions appear. So it's inverse of frequency in some sense.
So it's just set by the driving frequency
and the amplitude. The ratio of the driving frequency and the amplitude.
So it's really controlled from outside.
Yeah.
Any more questions? If not, let's thank.
Thank you.